Hi, everyone. Yeah, I'm Joachim Meyer from Saarland University, and the work I'm presenting on is mostly being done with IWOCL, to be honest, at Heidelberg University, but we did some more work at Saarland University as well. So what it's about is SPMD kernels. What is that? And yeah, well, it's a very general thing that we see very often in OpenCL, HIP, and so on. And I'll talk about how do we implement this on CPUs, and I'll try to bring you, give you information on 4 ways to actually implement this on CPUs. And 2 of them are library-only implementations, and 2 of them are compiler-based implementations. So I'll also show you that one of those compiler implementations has a semantical flaw, even though it's more or less widely used in practice these days. And I'll give you an example later, which like of one of the optimizations that you will need to do with the compiler approaches, and how to get actual good performance in the end. And finally, I'll obviously talk about performance. And as we've already seen today, since this is work that we did in HipSycl, and the work has been the results have been shown in the work by Marcel Breyer already, that if we do library-only stuff, it's probably going to be way slower than if we do compiler accelerated stuff. So let's dive into what a SPMD kernel is. So here you can see a SYCL parallel for ND range kernel. And this is a typical example of a SPMD kernel. But a SPMD kernel can also be implemented in OpenCL, HIP, and CUDA. And what makes a SPMD kernel special is you have a scalar part of the kernel. That is how you write the kernel. And we call that a work item in SYCL. And then we have a part that is saying, well, execute this multiple times on multiple data elements. And this is basically the full range then. And this full range can be split into smaller groups. We call that work groups. The interesting part is you can use the work items of a work group to cooperatively solve a problem. In this example, we have a reduction that is being cooperatively done by the work items of a work group. The cooperative part is usually done on local memory. So you write something to local memory and you read from local memory again to do the stuff cooperatively. To make this well-defined, though, you need synchronization between the work items of a work group so that the accesses to the local memory are ordered. We do that by using this barrier thing here in the middle. The semantics of this barrier thing are that if one work item of a work group reaches this barrier, then all the other work items of the work group have to reach the barrier before execution of the kernel may continue by any of the work items. And this requires that if one work item reaches the barrier, all the other work items still have to be able to make forward progress to be actually able to reach this barrier. And on GPUs, this is pretty simple. We just have many, many threads that are more or less implemented by hardware. And therefore, we get the forward independence, the forward progress basically for free. Also, the workgroup barriers are implemented in hardware, so it's basically free to do this. So, I mean, it's still costly, but still cheap. So how do you do this on CPUs? Well, as I said, we have 2 library-only ways to do this. And library-only, in this case, usually means that we just throw concurrency at the problem. One way to do it is just use 1 thread per work item. So we would need, if we have a work group of 256 threads, work items, we will need 250 threads as well. We can just do so by using OpenMP parallel 4, for example, and then for the barrier implementation, we just use OpenMP barrier. The problem with this, though, is that we will need many threads if we have many work items in a work group, and therefore we will get high scheduling overheads so that it's sometimes even infeasible to run the kernel. Also, since we're already parallelizing across the work items, it's kind of difficult to vectorize across them as well, which might be something that you might want to do. A way that is a little bit less overhead intensive, that is the default in HipSycl for the last few years, is to use a fiber per work item. In this case, you don't use parallelization across for a work group, and instead you actually execute multiple work groups at the same time using threads. And in one work group thread, you actually then use fibers, which are more or less like coroutines. So whenever you reach a barrier in the kernel, you just yield the next work item so that it can reach the barrier or the end of the kernel. This also makes it quite easy to optimize kernels that actually don't contain a barrier, because you never yielded a new work item before you exited the kernel. So if you exit the kernel, you can just loop over the rest of the work items because you know that you won't reach a barrier in the other work items of the work group. This then also allows you to vectorize across work items and so on. So you get pretty good performance with that if the kernel is barrier free. For the cases where we still have barriers, it's still a bit limited in the performance you can get. And let's have a look at that already. So here you see a Babel stream copy benchmark. On the left side, it's the original. On the right side, you see the same copy benchmark with just a barrier added at the end. So it's a pretty bad compute to barrier ratio, but anyway. As you can see, the OpenMP version that I just told you about performs quite poorly on this benchmark in any case. But the fibers version in the barrier-free case actually performs quite well because it has a rather high throughput here. But as soon as we add a barrier here, the performance really plummets. So you can see the difference here. And as I said, the nice thing about both of these approaches is that you can implement them without any compiler support. So you can just do so in a library-only fashion. So can we do any better when using a compiler? The answer is definitely yes. But how do we do that? Well, again, as with the fibers, we perform threading on the workgroup level and not on the work item level. And then we just loop over all the work items in this single thread. But as I said earlier, we need forward progress. So we can't just do this without any changes. So what we do is we actually split the kernel at all the barriers and only loop over the barrier-free parts. So when executing the loops after each other, we get implicit synchronization between those loops, which is actually exactly what we need for the barrier semantics. The nice part is these loops are pretty simple, and we have loop vectorizers in all the common compilers these days, so you can just have vectorization across the work items by performing loop vectorization. And as we already saw, the performance results will be quite beneficial, I guess. Yeah, I'll try to talk to you a bit about the two major implementations in compilers, how you can do that, like do the splitting of the kernels at the barriers. One of them is called deep loop fission and is being found in POCL, for example, but it was first presented in a CUDA CPU implementation called mCUDA. And what it does is basically pretty simple. It does just what I said before. So it starts by taking the first part of the kernel that comes before the barrier and wraps it in a loop. It also does this for this part here in the end. So it's pretty simple. But what's more difficult is the part in the middle where we have a barrier inside of a loop. So what it does here is it first executes the loop, like the loop header, which decides how often is this loop being executed for the first work item only. So this is why we have the local ID equals 0 here, basically. But the thing now is that this decides for all the work items that are being executed in this part, how often this loop should be executed. This works quite well for most kernels because the assumption is that if you have a barrier in a loop, the barrier has to be reached by all the work items of a work group the same number of times. So you could assume that the loop always will be executed the same number of times because otherwise you won't be able to fulfill this requirement. This works for most kernels, but there are edge cases where this doesn't work. And this is an example of this. So here you have a kernel with a loop that depends on the work item index. So for the first work item, we will execute this loop 2 times. For the second work item, it will be 3 times. For the third work item, it will be 4 times, and so on. This kernel would be illegal if we wouldn't have this if I smaller than 2 guarding the barrier down there. And now the question is deep loop fission able to deal with this kernel correctly? And it sadly is no, because as you can see, it will just decide how often this loop should be executed for the first work item only. And as the first work item only executes this 2 times, it will execute it only 2 times for all the work items, even though the other work items might need 3 or 4 times. So we will in the end get wrong results for this kernel. But there's another approach that we can use to split the kernel at barriers, and that is called continuation-based synchronization. So again, we have the same kernel on the left side, and we will just go through how we construct the resulting code, basically. So what the continuation-based synchronization does, it gives every barrier a unique ID. So we have, like, in the entry, we define the entry of the kernel as a barrier as well. That is 0. Then we have barrier 1 and barrier 2 and the exit of the kernel. We start at every barrier and go through the kernel with a depth-first search until we only find barriers again. So we would start here in the beginning for the first barrier-free part. We will start at the entry and find only barrier 1 in the end. Starting from barrier 1, we will go to barrier 2, or the exit of the kernel. That is this part in the end. And starting from barrier 2, we will again find barrier 2, or we will find the exit of the kernel. So that's the 3 barrier-free subchief keys. And these we can just wrap inside a work item loops. So this is, as you can see, these work item loops always iterate over the whole work group and don't have some special cases. Now the question is, how is it possible that we get the control flow back that we have on the left side? And that is by replacing the barrier calls by just storing the ID of the barrier that we reached. And we use this value then again to select which of the subchief keys, like the barrier-free parts here, we need to execute next. With this out of the way, let's have a short recap why this works and why the deep loop vision doesn't work for this kernel. For the deep loop vision, we have this loop in the kernel moved out of the kernel, so not every work item is able to decide for themselves how often the loop should be executed. Whereas in the continuation-based synchronization thing, we still have the decision how often this loop should be executed inside the work items, so they can decide for themselves how often to execute it. So with the base information out of the way, let's have a look at how we can make sure that this all actually works and is even faster. This is just one example of optimizations that need to be done. There are a bit more stuff in the paper, if you're interested. So one of the things that arise is work items can have private values. So if, for example, here in the left, you see a value that is read from global memory. And if we have a barrier between the definition of this value and the use of this value, we need to somehow retain the information for every work item. So what we do is we generate a stack array that has the size of the work group, and we just store the value to the stack array, indexing the stack array with a local ID. So this value 1 is being stored to the stack array, and in the second loop, we just load this value from the stack array again and use this new value that we loaded here. So therefore, we can retain the values of the across barriers. And now the problem with this is if we have uniform values, so this offset 1 here is a uniform value because it's always set to 0 for all work items. We would just store many zeros to this offset array. So that is kind of useless. So how can we optimize this? Well, we can use a value shape analysis or uniformity analysis. And by that, basically identify, oh, this is a uniform value. And if it's a uniform value, we just use a single value that we store this offset to. Then to actually make clear to the optimizer later that this is a uniform value, we load this value from the stack before the loop. So it's not inside the loop. So the optimizer obviously knows that for all the work items, this will be the same value. Another thing that's quite important for performance is that we retain contiguity information. So contiguity information means here we have again a uniform value offset 1. And if we add the local ID to it, this index 1 value will always be contiguous for all the work items. So for work item 0, it will be offset plus 0. And for the work item 1, it will be offset plus 1. And in theory, we will want this memory access down here to be vectorizable because it's a memory access, and yeah, it should be vectorizable really because the index 2 should be a contiguous value. But since we're loading it from the stack array, the optimizer really doesn't know whether this is a contiguous value. Again, we need to do a value shape analysis, identifying whether it's a contiguous value or not. And then we just trace back this value to only uniform and contiguous values, and we store all the uniform values to a stack value and just load the stack value again. And then we can just replicate the trace of instructions that led to calculating the index 2 in the second loop again as well. And with this, the optimizer is able to identify, oh, hey, this index 2 actually still is a contiguous value and therefore vectorize the memory access. So this alone gives us a speed up when implementing this in POCL for 7%, and in HipSYCL it gives us a gaming speed up of 17%, which is not too much, but it's noticeable. So let's talk a bit more about performance. So we were able to evaluate our HipSYCL and POCL implementations of these approaches on a bunch of systems. We have 3 ARM systems, 2 of them are HPC CPUs, and we also have 2 x86 CPUs that we tested that on. And this is the first result. So we have a reduction kernel, which has a rather bad compute to barrier ratio. And what this shows us is the speed up over the HipSYCL fibers implementation. So the deep loop vision is in blue, and the CBS implementation, continuous based synchronization, is in pink, I guess. So what we can see is that both the compiler processes are able to outperform the library-only implementation with up to multiple orders of magnitude. I mean, even 1,500 for some cases. So yeah, we can see that the DLF and CBS implementations are more or less on par here, and there are some wins for either of them. Now let's have a look at a different benchmark. This is a N-body benchmark. This N-body benchmark does have a way higher compute to barrier ratio. So here the speed ups are way less noticeable. So as a takeaway, if you need to do library only stuff, make sure that your compute to barrier ratio is really high so that you will get a kind of good performance in the end. Apart from that, we can see that the CBS implementation usually outperforms the DLF implementation in HipSYCL. And that is also with all the other benchmarks summarized. We can see that our CBS implementation is able to outperform the DLF implementation. But we also did this in POCL as well. And we just did the POCL implementation basically as a litmus test to make sure that our CBS implementation, which is correct, and in which the deep loop vision implementation is not in all cases, is actually not much slower than the deep loop vision implementation. So as you can see again here, even in POCL, the CBS implementation usually is faster than the deep loop vision implementation for a DGEM benchmark, which is, I don't know, kind of what we hope for. Yeah, there's some more benchmarks that we did in POCL, as I said, just to make sure that we don't miss anything. And what is interesting here is that the HPC ARM CPUs, the A64FX and the Thunder and Marvel Lake 2, do perform pretty bad with CBS for some GEM benchmarks. And the only way I can, I don't know, explain this personally is that they probably have issues with the a bit more complex control flow that CBS has. And it's, for me personally, I found it interesting that the M1, which is also an ARM CPU, doesn't have this problem. So it really seems to be a problem in the front end of the CPUs. So overall, in POCL, we see that the CBS and Deep Loop Vision view mean speedup is exactly 1, which is just what we hoped for. And in some cases, actually, CBS is able to outperform Deep Loop Vision. So to summarize, we've seen that we can implement SPMD kernels on CPUs in a library-only fashion. If you want performance in a barrier-free case, the fibers implementation is already good, but compiler approaches will obviously also be a good performing contender. If you want performance with barriers involved, library-only implementations probably won't do it. So you will probably want to do some way of compiler approaches. And yeah, on the HPC ARM CPUs, the Deep Loop Vision kind of outperforms CVS, but as I said, the Deep Loop Vision is not quite able to outperform to cover the full barrier semantics. So my personal recommendation is to use continuation-based synchronization in most cases. So thank you so much.
Thank you. Any questions?
So now we have coroutine in C++. Have you tried to use C++20 coroutine instead of boost fibers?
We haven't tried that yet, but it would be great because then we get rid of the boost dependency in HipSYCL. So
I had a question. So you mentioned HipSYCL and POCL. How could I try this for my applications today? Do I need to use the POCL backend to HipSYCL, or how does all the pieces fit together if I want to try it?
So they are independent of each other. In HipSYCL, you can just go to the download HipSYCL and just say, I want the accelerated workflow. That will obviously mean you will have to use Clang, as we heard earlier. By default, that's already happening. With POCL, it still defaults to using the Deep Loop Vision approach, but it's also upstream that you can use the CBS if you want to by just using a environment variable.
Okay, great. Well, thanks to our speaker again. Thanks for the great talk.